Games theory is the application of structured, formal logic to solve problems. Games theory may use rational choice, which is a decision-making approach that assumes the decider is seeking to maximize ordered preferences. The assumptions of rational choice are interdependence between the different actors. The actors have preferences. The preferences that are listed are exhaustive, and that the individual actors are trying to maximize some goal. Now, outcomes in the international system are typically the result of strategic interaction, which is the intersection of the actions of two or more actors. Rational choice uses games theory to represent these strategic interactions and to test theories by logically examining puzzles. Games theory is, in its essence, simplification. It has realistic assumptions that represent the core assumptions of real situations, but they are dramatically simplified in order to facilitate testing. Many of the models in games theory have interesting implications and give us insights in international relations. Now here we have a strategic form prisoner's dilemma game. This is an example of a cooperation game and is intended to demonstrate just how difficult cooperation can be. In this form, we have a strategic form representation of the game. You have, representing the two rows of cooperation and defection on the left, you have player A. And player B represents the choices of cooperation and defection in the two columns. What we want to do is focus on the payoffs, which are contained in each of the cells. I've conveniently put a diagonal line to show that the top right payoff applies to player B and the bottom left payoff applies to player A. Normally, I would have to indicate the priority of the players with regard to their payoffs. The payoffs in the cells here indicate time spent in jail. In other words, the lower the payoff, the better. 6 years is the worst outcome. 5 years is then the less worse outcome. Then there's 3 months in jail, and then there's no jail time at all. And these values basically are produced from the intersection of the choices made by the players. Each of the choices is called a strategy. Now here we see player A having a choice between cooperation or defection. So cooperation implies the green payoffs and defection implies the red payoffs. It's not yet known what player B's choice is going to be. And so we can't know what the outcome payoff is going to be for player A. Here we have the two strategies for player B. There's the cooperation column and the defection column. Again, they have payoffs specified for the two different strategies, but it's unknown what payoff will occur because they depend on the choice of player A. Now, prisoner's dilemma is meant to, this strategic form is meant to represent a situation where two individuals or more go to rob a bank. But before they can rob a bank, they're caught, and then they're isolated. And so there's no actual robbing of the bank, but there could be intent to rob the bank. So the interrogators working for the police isolate the two prisoners and then tell the prisoners, well, here's a payoff. If you tell us that the other individual was going to rob the bank, we're going to let you go free. Now this is a defection with respect to cooperating with the other thief, because the two thieves rationally should cooperate. If they cooperate, then rationally they're going to reduce their collective punishment, because they're both going to say, you know what, A will say that B was not there, to rob the bank, and B will say A was not there to rob the bank, and they're going to go to jail for 3 months for trespassing. But there was no robbery. Now the prosecutors absolutely need to punish someone, so if one of the individuals accuses the other of being a thief, but the other does not make a reciprocal accusation, one of those individuals who fingered the other will walk free with 0 jail time, whereas the other one will go to jail for a very long 6 years. If the two individuals, however, finger each other, then there's less of a desire by the prosecutor to make an example, because basically everyone's going to jail, and so both of the individuals get 5 years. So this is the situation that is represented here, and it captures a lot of events in politics, which is why we use it. So the Nash equilibrium is a theory about a stability that's achieved when both players make choices, and after the choice is made, they no longer have any incentive to change their choice. So what we want to do is solve the game by identifying the Nash equilibrium, because that's going to tell us about how the game is going to end. Now the way we do this is we determine what is the dominant strategy for each player. Now a strategy is dominant if it dominates other strategies. If a strategy is dominated, then we eliminate it, because a player will never choose a dominated strategy. They will stick with their dominant strategy. So let's take a look here. For player A, there are 2 strategies: cooperation and defection. Player A can choose to cooperate and get the green payoffs, or choose defection and get the red payoffs. The way that we determine a dominant strategy is it's a strategy that is superior to the other strategy in terms of payoffs in every cell. So let's compare defection and cooperation. We examine compare the payoffs with respect to the other player's strategy. So let's take a look at the column of cooperation for player B. We can see that players B cooperation column has the payoff for player A for cooperation and defection. Player A's payoff for cooperation is 3 months in that column. Player A's payoff for defection is 0 time in jail. So what's better, 3 months in jail or 0 time in jail? Obviously 0 time is better. So player A will choose between these 2 cells to defect. We then look at the next column of player B, the defect column. And we see there that player A has 6 years in prison in green if they choose to cooperate. If they choose to defect, player A has a payoff of 5 years in red for choosing the defect strategy. So which is the better choice for player A? 6 years in jail or 5 years in jail? Well, player A wants to minimize their time in jail, so player A is going to choose 5 years over 6 years. So in both cells, defection is superior than cooperation, because 0 time in jail is better than 3 months in jail, and 5 years in jail is better than 6 years in jail, so player A will choose to defect. Now player B also has 2 strategic choices. Player B can cooperate or defect, and there are payoffs for each of the choices. Now we compare the payoffs according to the cells of the other player. So we look at player A's cooperation row, which is the top row. So player B will compare the payoff of cooperation, which is 3 months in green, against 0 time in jail in red. Which is the superior payoff? For player B, 0 time in jail is the superior choice. We then compare the payoff for player B in the defect row for player A. And player B here has a payoff for green cooperation of 6 years. Player B also has, for defection, the red choice of 5 years. And which is superior? 6 years in jail or 5 years in jail. Player B would like to minimize their time in jail, so player B is going to pick 5 years as the better payoff. So in both cells, defect is superior to cooperation. So player B will always choose to defect. Defect is the dominant strategy. It dominates cooperation. Cooperation is the dominated strategy, and so it would be eliminated. It would never be chosen. So the final step in determining the Nash equilibrium is to find the intersection of the two strategies that are dominant and dominate all the other strategies. For player A, we determined that was defection. It provides a superior value in all of the cells. For player B, the superior strategy is also defection. And so we look at the intersection of those two choices, and the strategic interaction outcome is that both players are going to spend 5 years in jail. Now, clearly, this is a suboptimal outcome. They could have both spent 3 months in jail. But that's not what a single play of the game's Nash equilibrium would suggest is the outcome. Now remember, the definition of the Nash equilibrium is that neither player has an incentive to change their strategy. Now imagine that player B does not change their strategy. So player A would think, well, you know what? I'm going to go back and change my strategy from defection to cooperation. But what's going to happen with the payoff? That would mean player A is going to go from 5 years in jail in the defection strategy, and when they switch to the cooperation row, it'll shift them to 6 years in jail, right? Because we have the strategic choice of player B remaining as the defection column. So player A is not going to change their choice. They're going to stay with 5 years because 6 years is worse. Player B also has the same symmetrical choice. If they shift from the defect column to the cooperation column, they're going to go from 5 years to 6 years in jail, which is not in their payoff interest. They want to minimize the time in jail. So player A and player B are not going to change their choices. Therefore, we have a Nash equilibrium. So you're going to have the outcome of both player A and player B going to jail for 5 years because they were unable to communicate their coordination of not fingering each other and therefore staying in jail for 3 months. But the promise of having a chance of spending no time in jail at all, and the fact that defection dominates cooperation and strategy, led them to make this suboptimal choice. Now, prisoner's dilemma occurs in many political situations. Here I have the IR, International Relations Representation, where the prisoner's dilemma can look at arms racing. Now, both players can disarm and you'll have peace. If both players arm, it could ultimately end up in war. But players generally won't choose to disarm because there's the danger they can be exploited. If one arms and the other disarms, then they could be conquered by the other. So it's the fear of being exploited that leads them to not cooperate, in fact to arm, not disarm, and then risk the outcome of war. So mutual disagreement is a collectively and individually better outcome, but the insecurity created by the inability to make promises leads both states to pursue expensive and dangerous armament. You can imagine how this could apply in domestic politics as well, or institution building. Another game is the stag hunt. This is one formulated by Jean-Jacques Rousseau in his attempt to characterize cooperation. So you have a party of hunters, right? In this case we have 2 hunters, but in Rousseau's original example there were many hunters. If the 2 hunters cooperate, they can catch a large stag. You can see a picture of it here. If the hunters don't cooperate, they're not going to be able to catch the stag because the stag will escape in one of the holes left by one of the distracted hunters. Now the dilemma occurs when one hunter sees a rabbit. If that hunter chases the rabbit, he's going to eat less than if he caught the stag. And the other hunters are going to eat nothing. But the hunter is still going to eat. They're going to catch the rabbit. But in the process of chasing the rabbit, they're going to create a hole through which the stag is going to escape. Now, every hunter knows that every other hunter has the choice of a rabbit. And so they're going to chase a rabbit as well to secure at least a minimum meal of a rabbit. But if every hunter is chasing rabbits, then there's going to be no one chasing the stag, and it's going to create so much noise. The rabbits are also going to escape. And so no one will eat anything. Now, the preference here is to cooperate to capture the stag in terms of the payoffs. The stag provides the most food, then the rabbit provides a lesser amount of food, and nothing is the worst possible outcome. Now, this situation simulates interactions in which suboptimal outcomes are made more likely by the fear not of exploitation or backstabbing, but by the fear of abandonment. Now, let's try to find out what the Nash equilibrium is here. So for player B, there are two choices. There's C for cooperation and D for defect. So we always want to compare the categories from the other player strategies. So for player A, we have the cooperation row. So player B is going to compare the payoff of a stag versus a rabbit. Which is better? Obviously the stag is better. And for player A's D row, player B has two payoffs: 0 food, because the stag has been allowed to escape, and 0 food because the amount of noise of everyone chasing the rabbits has allowed the rabbits to escape. So here there's an indifference. When you have indifference, you're not going to be able to say that one strategy dominates the other or is dominated by the other. So we refer back to the original cell. So stag is superior to rabbit. 0 creates indifference with 0. And so player B will always cooperate. Player A has the same choices between cooperation and defection. In the first column, which is player B's cooperation column, player A has a choice between a stag and a rabbit. Clearly the stag is the better choice. In the next column of player B's defection, player A has a choice between 0 payoff and 0 payoff, and there's an indifference there. So player A is going to choose cooperation over defection because stag is superior to rabbit and 0 is indifferent to 0. So player B and player A are both going to choose cooperation. It's going to intersect over the stag cell, and so they should cooperate. Now, logically, again, the Nash equilibrium is that neither player has an incentive to switch. So player A, if it's going to switch, is going to leave the stag for a rabbit, and if player B switches, it's going to leave a stag for a rabbit. In neither case are they benefited by getting a greater payoff. So this is the chicken game. It's sort of an image from 1950s movies. You've got a road at a high school, and you've got two cars that are driving towards each other down a street as a test of courage. The driver that drives straight and does not swerve away is seen as more courageous because they're risking death. If a driver were to swerve off the road to avoid a collision and the other car were to drive past them down the center of the road, swerving would make the driver look like a chicken. In other words, they're scared of driving down the center of the road and dying. If both drivers swerve off at the same time, they're basically wimps. They're not chickens because they're not facing another driver that stayed down the road, so them turning off is less severe. But they're definitely not seen as courageous. They're wimps. So you can imagine, there's sort of Fonzarelli, the Fonz, or there's James Dean, two cool dudes from the 1950s driving towards each other. In Rebel Without a Cause, there is a game like this, but James Dean actually and his competitor are driving their cars close to a cliff edge rather than driving their cars towards each other. So the preference ordering is hero first, where you drive the car down in the center of the road regardless, then wimp, then chicken, and the worst possible outcome is death, where two cars drive into each other in the middle of the road. In order to be a hero, you must risk death. And so this is a different structured game than the prisoner's dilemma. Now, the chicken game simulates situations in which the cost of mutual defection is catastrophic, like, for example, nuclear war, or in international political economy, raising tariffs so that both economies are wrecked by a lack of trade. But this game is also characterized by a high payoff for exploiting the other actor. So this is very often the model used in brinkmanship, like the Cuban Missile Crisis. There is no dominant strategy in a game with this type of characteristic. So we cannot solve it using a normal, pure, dominant game strategy. So to solve this, we're going to look at other techniques. But for now, let's see if we cannot find a dominant strategy. So for player A, there are two strategies, cooperation and defection. And let's compare those two with respect to player B's strategies. So for player B's strategy of cooperation, player A has two choices, cooperation or defection, and there are two payoffs, hero or wimp. Now hero is worth more than wimp, so player A should choose defection. When player A goes to the defection column of player B, player A has a choice between dead and chicken. Dead is always worse than chicken. So here, player A should choose cooperation. So there's a problem. Depending on which choice player B makes, player A does not have a dominated or dominant strategy. There's actually a cycling phenomenon here where player A is going to change their choice based upon what player B chooses. Now player B has the same payoff dilemma. Player B has two strategies, cooperation and defection. If we were to compare the choices using player A's cooperation row, we would see the choice between hero and wimp. And player B would always choose hero over wimp. In the next row, player A's defection row, player B has a choice between chicken and dead. And player B will always choose chicken over dead. So we have a problem. If player A and player B choose, for example, to mutually defect, which is to go for hero, but the intersection of defection and defection is death, do we have a Nash equilibrium? Remember, a Nash equilibrium is when a player makes a choice and then doesn't have an incentive after to change that choice. So if player A currently has the payoff of dead, because player B has also chosen to defect, if player A switches their choice from defection to cooperation, they go from dead to chicken. Right? Which is a good payoff, because chicken is better than dead. Now if player B was also going to make that same choice and they were to switch to chicken, then we have a case where player B chooses cooperation and player A chooses cooperation, and now we're in the wimp and wimp cell intersection. Now we can ask the question again, do they have an incentive to change? Well, player A is going to go, well, I'm in the wimp category of cooperation. If I revert to a defection strategy, I'm going to go from wimp to hero. So player A is going to go from cooperation to defection and go to the hero. It's going to choose the defect strategy. Player B is going to do the same thing. They're going to choose hero over wimp and go to defect. And so we're back to the intersection of defection and defection where we've got mutual death. So we cannot solve the chicken strategy by using dominant or dominated strategies. So what we're going to do now is look at three other solutions called the best response analysis, minimax solutions, and finally the mixed game strategy. So here we have a strategic form game of two players or two states in a confrontation. Each player has four strategies or choices. Player B's got negotiate, attack, ally, and surrender, and player A has also the same choices, negotiate, attack, ally, and surrender, and there are the respective playoffs. Both players have the same preference for the higher value over the lower value. So the first step we would apply here is try to eliminate dominated strategies. So let's go ahead and do that. So for player B, we could compare negotiate and attack. And we can see that 2 is better than 1, 2 is better than 1, 1 and 1 are the same, and 3 and 3 are the same. So player B would never choose to negotiate because the values in attack are equal or greater. We could also compare ally column versus surrender column, the two strategies of player B. We could say that 3 is better than 0, 1 is better than 0, 3 is better than 0, and 3 is better than 0. So player B would never choose to surrender. Okay, so we're going to rotate and look now at player A. So player A has a choice that's much reduced because cells have been eliminated for both players. So player A would compare to negotiate or attack. And we can see that for the choice of negotiate and attack, 1 and 1 are the same, and 2 is better than 0. So player A would never choose to negotiate. We could also compare alliance and surrender for player A. We can see that 2 is better than 0, but 0 and 0 are equivalent. So player A would never choose to surrender. So what we have left with are the 4 central cells. So let's see if we can find some dominated strategies there. So for player B, we can see that 2 is better than 1, but 3 is better than 1. So we would have cycling here. There is no dominated strategy for player B. So for player A, we notice that 2 is better than 1, but 2 is better than 0. So we have the same problem. These 4 central cells have no dominated strategies. And so we have now our 4th solution, which is called the mixed game strategy. This actually has a mathematical proof from John Nash, which shows that this is the most efficient way of maximizing the gain for a particular player, unless that player has a spy in the other camp. So when a game has no dominant strategies and there's no equilibrium from the best response analysis or from the minimax method, a mixed game strategy will always exist. It consists of a probabilistic strategy in which the player plays different strategies with a certain probability. The logic of a mixed game strategy is to choose a combination of strategies that neutralizes the opponent's ability to exploit the differences in their payoffs. So if a player receives higher payoffs from one choice over another, then the opponent will offer that choice less frequently. Essentially, the mixed game strategy is neutralizing the opponent's ability to exploit the differences in payoffs by making them indifferent between their different strategies. And this is achieved by making available the lower payoff cells more often than the higher payoff cells to the opponent. And there are theorems that demonstrate that, amazingly, mixed game strategies are the optimal possible outcome unless you have access to secret information as to what the other player is going to do. So by analogy, if you have a boxing match and you're facing off an opponent with 2 arms and one arm is preferred by the other, so let's say the left hand is stronger than the right hand at swinging, you want to alter your own defensive behavior to minimize the opportunities for the stronger left hand and to compel that player to use their weaker right hand more often. This doesn't mean that you're going to do better if you knew how the opponent was going to swing, but that on average, as the opponent's playing, you're able to minimize their advantage. Now the outcome is that each player will do better playing their probabilistic strategies irrespective of what the other player does. That is incredibly counterintuitive. So you're going to be looking at the other player's values, not your own. If both players follow their optimal probabilistic mixed game strategy, then the probabilistic intersection is the mixed game strategy Nash equilibrium. Obviously, a given player will do best if they have a spy that can find out what the strategy the opponent's going to play in any given turn. But in the absence of a spy, the mixed game strategy provides the best possible playoff for the player that makes use of it. And any player that deviates from the probabilistic strategy will receive less payoffs than if they had abided by the mixed game strategy. So what you see here in front of you is the 2x2 cell that remained after we eliminated the dominated strategies. So you'll see that there's a preference, which is 3 is greater than 0. And player A has two strategies, attack and alliance, and player B also has two choices, attack and ally. Now I've put variables in there which are traditionally used. And we have theta 1, 1 for player A's attack strategy, theta 1, 2 for player A's alliance strategy. Player B's attack strategy is theta 2, 1, and player B's ally strategy is theta 2, 2. These could just as easily be represented by x and y's. But I've chosen to use these variable names because it's what's traditionally done. Although you are welcome to use simpler variables like x and y or a and b. Now, theta 1, 1 is not a number. The values are not multiplied or added to anything. It's a name, so it stays like that throughout the entire algebraic process. Now, the key logic to this is you're going to be looking at the opponent's values. So, player A is going to create an equation that needs to be solved algebraically. That equation is made up of two formulae which equal each other. Each of those two formulas are going to contain the two variables that player A has, attack versus alliance. So these variables will be applied to the opponent's values, not player A's values, but player B's values, the values of the opponent, because it's the opponent that we're trying to make indifferent. So we're going to alter our behavior to make the opponent indifferent between their choices. So the formula is going to be theta 1, 1 times 2, which is the opponent's value, plus theta 1, 2 times 1. And we're going to make that equal to theta 1, 1 times 1 plus theta 1, 2 times 3. And we're going to make those two formulae equal to each other, and then we're going to solve it algebraically. And we're going to do the same for player B. So we're going to take theta 2, 1 for player B and multiply it times 1 plus theta 2, 2 times 2. And then we're going to make it equal to theta 2, 1 times 2 plus theta 2, 2 times 0. And we're going to solve those two equations separately, independently, and we're going to isolate the variables, and we're going to end up with a number. And the number is going to tell us how often we play theta 2, 1 versus theta 2, 2, and how often we play theta 1, 1 against theta 1, 2. So we're not going to get a definite answer, we're going to get a probabilistic answer in which we distribute how often we play theta 1, 1 against theta 1, 2. The implication here is serious. It means in order to do the best possibly, according to the theorem that proves this to be true deductively, you have to roll dice. So there is no genius in a decision maker. There is no general that can automatically come up with the best brilliant answer after thinking about a problem for 3 or 4 minutes. You have to take out dice and roll. And if you deviate from the process of randomly selecting between the two choices according to the probabilities, you will do worse than if you roll the dice. So never deviate. Important decisions need to be resolved randomly if it's a mixed game strategy. And if you don't do it that way, you will do worse. This is all very counterintuitive. It's incredibly controversial. You would never admit that a business decision or a boxing match or a war strategy are decided randomly, or that nuclear weapons have to be launched in a random fashion. But this is the emergent property that we can observe in nature, and the theorem that proves this to be the most efficient. An important assumption to solve the algebra of the mixed game strategy is what I call the pizza rule, which I'm going to need you to agree with before we can proceed to solve the algebra. The essential problem is that we can't solve an equation with two variables. So we need to come up with a solution to reduce that to one variable. Now the pizza rule is basically an observation about how we distribute a single object. So the whole pizza is equal to my slice of the pizza, x, plus your slice of the pizza, y. Now we can rearrange this by, for example, subtracting from both sides of the equation my slice of the pizza. And what that's going to do is shift my slice with a change to a negative value to the other side of the equal sign. So the whole pizza minus my slice is equal to your slice, right? This is intuitively true, and it's algebraically true. Now, symbologically, we would represent this as y is equal to 1 minus x. Or your slice y is equal to the whole pizza in red, 1 minus x, which is my slice. Or in my variable choices, it would be theta 2, 2 is equal to 1 minus theta 2, 1. Okay? This needs to be understood and accepted before we proceed to the solution of the algebraic equations. And I think you would agree this is very obvious and intuitive. So here we have the equations that we constructed earlier. So here for player B on the top, we have player B referring to the values in player A's strategies. All right, we constructed exactly this equation in the previous slides. So player A right is theta 2, 1 plus 2 times theta 2, 2. And player A's left is 2 theta 2, 1 plus 0 theta 2, 2. Now this here is the pizza rule, which is theta 2, 2 equals 1 minus theta 2, 1. And you agreed to this in the previous slide. All right, so we take the two formulae, we put them together, and we get this equation, okay, which we now need to solve algebraically. Now the first step is substitution using the pizza rule. We are going to remove theta 2, 2 out of this equation and replace it in brackets with 1 minus theta 2, 1. Now the effect of this is to have only one variable in the entire equation, which you can see here, and that's going to make it solvable. So the theta 2, 2 is against the 0 is simply going to get canceled out, because 0 times anything is equal to 0. And we distribute the 2 into the brackets, we multiply in, and so we're going to get theta 2, 1 plus 2 minus 2 theta 2, 1 is equal to 2 theta 2, 1. And if we work this out algebraically by adding and subtracting values on both sides, recall high school, we're going to end up with 2 is equal to 3 theta 2, 1. And then we divide both sides by 3, and we're going to end up with 2/3 is equal to theta 2, 1. Now here we're going to use the pizza rule again. We know that the whole pizza is equal to your pizza plus my pizza, or that theta 2, 2 is equal to 1 minus theta 2, 1. So theta 2, 2 is equal to 1 minus 2/3. And that means theta 2, 2 is equal to 1/3. So these are the values we're going to put in that 2 by 2 table. Theta 2, 1 has to be played 2/3 of the time. Theta 2, 2 has to be played 1/3 of the time. 2/3 plus 1/3 is equal to 1. So that's the distribution between the two choices. You can't pick a strategy. You have to randomly make the choice by rolling dice or some similar method. So for player A, in the bottom half of the slide, we do the same type of calculation. Player A is looking at player B's values. We've got here the two formula that we constructed in the previous slide, 1 theta 1, 1 plus 3 theta 1, 2. And the other formula is 2 theta 1, 1 plus theta 1, 2. And again, we have the pizza rule. Theta 1, 2 is equal to 1 minus theta 1, 1. We put the two formula together into this equation. We have two variables. We can't solve the equation with two variables, so we substitute in to get rid of theta 1, 2. We replace theta 1, 2 with 1 minus theta 1, 1 in brackets. And that's what we have here. So we multiply 3 into the bracket, and that's going to give us 3 times 1 is 3, and then 3 times minus theta 1, 1 is minus 3 theta 1, 1. Here we're going to subtract 1 theta 1 1 from 2 theta 1 1. That's going to leave us a theta 1 1 on the line below. And algebraically, we're going to move the terms around by adding and subtracting the terms to both sides of the equation, and we're going to end up with 2 is equal to 3 theta 1 1. And algebraically, that'll end up being theta 1 1 is equal to 2/3. And we use the pizza formula. Theta 1 2 is equal to 1 minus theta 1 1. So that's going to leave theta 1 2 as 1/3. Now, it's not necessary that player A and player B both have a 1/3, 2/3 split. There's versions of this mixed game strategy where one player has a 3/4, 1/4 split, and the other player has a half and half split or a 1/3 and 2/3 split. Many different combinations. So you don't have to have the same distribution between the strategies for both players. So this is how you achieve the mixed game strategy. It tells you to play randomly, and it has a mathematical proof, and so it's completely superior to either best response analysis or... And here you can see the verification for player B. 2/3 plus 2 times 1/3 is equal to 2 times 2/3. This is reinserting the values into the equation. And then for player A, 2/3 plus 3, open bracket, 1/3, close bracket, is equal to 2, open bracket, 2/3, close bracket, plus 1/3. And so this is simply taking the equations that we created by combining the formula and inserting the values to confirm that the equations are equal on both sides. Iteration is a repetition, and it's specifically the effect of repetition on games between opponents. If players receive benefits, then as they look into the future, and this is termed the shadow of the future, because a player can look in the near future or the far future depending on their particular perspective. So players can see the benefits to cooperation accumulating across time into the future and are therefore more likely to cooperate. So if you were to play the prisoner's dilemma, for example, repeatedly, it actually ends up resulting in mutual cooperation. However, if the prisoner's dilemma game has a definite end, then cooperation may not be the result. To determine the Nash equilibrium, you would solve the very last prisoner's dilemma game. The Nash equilibrium for a prisoner's dilemma, of course, is mutual defection. Then, given that the last game has resulted in joint defection, there's then no shadow of the future or anticipated benefits of cooperation. And so the second to last game also has a Nash equilibrium of joint defection. And this Nash equilibrium of joint defection is extended to the third to last game, the fourth to last game, and so on until the very first game, which will also result in defection. So it's not always true that iteration leads to cooperation. But most of the time when two players are cooperating, the future is infinite and indeterminate, and they don't see an end, and so they don't follow this logic. If they look short-term into the future, they get some benefit. You know, maybe they look 5 years into the future and they get 5 benefits of trade. But maybe the advantage of exploiting and backstabbing today is worth more than all the payoffs for the next 5 years. And perhaps the gains you get next year are worth only half of what they are this year, and the gains in 2 years are worth only a quarter of what they are this year. And so the values drop off pretty quickly. But sometimes, and that's called the discount of the future, but other times people look very far into the future, hundreds of years, and anticipate benefits, and therefore act with much greater wisdom and patience. One type of application of games theory is the two-level game. For state leaders, interstate negotiations are most often made more complicated because leaders are playing two games at the same time. They're playing a prisoner's dilemma against the opposing state. They're trying to play a game in which there's opportunities for exploitation, like in economic negotiations, the dumping of goods on a market, for example. And it's exploitation that's similar to a prisoner's dilemma game. But the politicians are also playing a chicken game against their own domestic political opponents. They're basically daring their opponents to compel them to make a bad choice that results in a disastrous economic outcome. So they're playing against each other for the popularity in their legislature. As both leaders are facing the same level of complexity at the international level, they are in effect three games played simultaneously. You're playing a game against the other opponent, you're playing a game against your own population, and so this can be characterized as a third type of game. And this we call a two-level game. Now, a surprising finding is that the weaker a leader is with respect to their own domestic opponents, the stronger is their negotiating position for international negotiations, since they can threaten the opponent state to soften their position lest they be overthrown and no negotiated agreement results at all. So your weakness, in fact, becomes your strength because you can compel your opponent to give you favorable terms in order that you achieve your negotiating position. The problem happens when all parties are playing weakness, and if no one relents and cooperates, then ultimately there is no agreement achieved. Another type of game structure is the extensive form game. Extensive form games have a tree structure with decision nodes in which players make choices sequentially between the different branches. Decision nodes indicate where players may choose different options. The model presented here examines decision making during the Cuban Missile Crisis. So how do you solve an extensive form game? Well, there's a theorem called Zermelo's theorem. And it says that extensive form games are solved by reverse induction. And this consists of two steps. In step one, you start at the end, which in this particular extensive form game is at the right. Meaning, you look at the closest decision nodes to the end of the game, and you select the highest payoff for that decision maker. You then proceed through each layer of nodes until the beginning of the extensive form game, which here is represented on the left. And you only use the paths that were selected by the lower decision modes on the right. In step two, once all of the decision paths have been chosen from each node, you determine the Nash equilibrium outcome by following the remaining paths fully linked to the final payoffs from the left to the right. So in this particular representation, we have an extensive form game. We have a soft line Soviet action. In other words, we have a Cuban Missile Crisis in which we assume in this particular form that the Soviet Union is not particularly aggressive. So as usual, the higher payoff is the better payoff. And you can see here the payoffs are color-coded. So if we look at the extreme right decision node, we have those squares that are black, and they're result nodes with the payoffs. But the first decision node occurs for the USSR as we move towards the left. And the USSR at that node has a choice between withdraw and defy. Now, how does the USSR choose, according to Zermelo's theorem? Well, the USSR is going to look at its payoffs. It's got a payoff of -4 for withdraw and -8 for defy. So the Soviet Union will choose always to withdraw because -8 to defy implies a fear of nuclear war. So here we would draw in the line that, pointer options, so this is the line that would be chosen. Defy will never be chosen. So we now go to the next decision mode towards the beginning, which is the US, which happens at the extreme left. Now the US has two choices. Either they don't threaten, and it gives them a color-coded payoff of -2, or they do threaten. Now, the payoff for threaten is going to follow the choice made by the Soviet Union at their decision mode, which is withdraw. So it brings the US not to the -10, but to the 1 payoff. Now, since a 1 payoff is better than a -2 payoff, the US will select threaten. And now, in the final step of Zermelo's theorem, we link up those paths. And we can see that the outcome is going to be the US threatening rather than not threatening, and then the USSR withdrawing rather than defying, with a payoff to the US of 1. And we can see here the application of the reverse induction result, which is what we produced just earlier. Here we have a hardline Soviet action. In other words, we have a different personality for the Soviet player. So the payoffs are different. So again, starting with Zermelo's theorem, we look at the node that's closest to the end, which in this case is the USSR node. And the USSR has two payoffs. They can defy for a -4 or withdraw at a -8. Probably because of reputational costs, the Soviet Union would prefer to defy. So in this instance, this is the path that the USSR would choose. Now, following Zermelo's theorem, we then go to the next decision mode, which is the US. Now, the US has two payoffs. They have a -2 for don't threaten and a -10 for do threaten, which passes through the Soviet choice of defy. So the Americans are going to go for the better payoff, which is -2, and they're going to choose don't. And so the Soviets never do make a decision, because the US decision node bypasses the Soviet decision and goes right away to the payoff of -2 for the US and 2. And we can see here, in the application of reverse induction, the ultimate outcome of the US's choice to not threaten. Now, nature may be attributed a decision node to model instances in which one player has uncertainty about the nature of the opponent. In the model presented here, nature represents the uncertainty node for the American decision makers of whether they are dealing with a soft line or hard line Soviet decision makers during the Cuban Missile Crisis, a distinction that has serious repercussions. The undifferentiable decision nodes are enclosed in a single information set, as presented here. And so here you have the Soviet hard line, which is a probability of p, and the Soviet soft line, which is probability of 1 minus p, which is the remaining probability. So here we have Zermelo's theorem applied to the extent that it can be applied, but because we don't know the nature of the Soviet actor, and we don't have probabilities for those distinguished personalities, we can't come to a solution in this model. So here we have an extensive form game representing a hostage taking. So in this game, chance plays first, determining whether the terrorists are soft line or hard line. Militants then decide whether to take hostages or not. Then the government chooses whether to negotiate with the terrorists or not. And then the terrorists choose whether to release the hostages or not. So this is the sequence of decisions. It's not the sequence of solutions. Zermelo's theorem, using reverse induction, would still be applied. So here we have a probability of 0.25 of the terrorists being hardline, and a probability of 0.75 that the terrorists are soft line, with all of the implications for the resulting probabilities. So in order to solve the extensive form hostage game, it consists of first multiplying the individual payoffs by their probabilities. On the right side, there's a column which is the militant's utility. U means utility, it's another term for payoff, and utility for the government. For those payoffs that are associated with a probability of 0.25, those payoffs are multiplied by 0.25, whether they're negative or positive, and you get the new values in red for both the militants and the government. For those payoffs that come off of the branches of the extensive form tree that are associated with a probability of 0.75, you multiply the payoffs, both positive and negative, of both the government and the militants by 0.75. And those are the red values. They're the updated values that are the result of the multiplication of the probability times the outcome. Now, in order to solve this through reverse induction, according to Zermelo's theorem, we have to start with the decision nodes that are farthest to the end, in this case, to the right. So there are 4 decision modes. the militants need to decide whether or not they're going to release the hostages. So starting at the decision note at the top, we have the militants having a payoff of a quarter versus a half. And a half is better, so they're going to choose to release the hostages. In the second decision mode, they have a choice between a minus 3 over 4 or minus half. Minus half is the less bad choice, so they're going to choose not to release the hostages. In the third node, the militants have a choice between a payoff of 1.5 or 3/4. 1.5 is better, so they're going to release. And in the fourth node, the militants are going to choose between minus 2 1/4 and minus 3. And minus 2 1/4 is the less bad choice, so they're going to choose to release. So these are the four choices. The next set of choices go to the government. Now here we have an information set. That's the dashed line. The government has to combine their choices because the government doesn't know what kind of adversary they're dealing with. So we have to take a probability of both of the payoffs. So the government payoffs have already been multiplied by 0.25 if they're associated with that part of the tree, or with 0.75 if they're associated with that part of the tree. So we can see those values in red under YouGov. Now the government, when it makes a choice, it has to make it consistently for both the hardline militants and the softline militants. So whatever the choice is being made, it has to make it consistently for both. It has to make the same choice for both, not knowing what the precise identity is. But it does have the probabilities. So since the payoffs have already been multiplied by the probabilities of being soft or hardline, the government payoffs are simply the average of the decision to pay versus the decision not to pay. So the decision to pay for both the soft and the hardline terrorists, this is the pay line, and you simply follow it down to the government's utilities over here, following the paths as indicated by Zermelo's theorem. We have here the payoff to pay as minus half and minus 1.5 divided by 2. And that's going to give us a payoff of minus 1. So the payoff to pay is going to be minus 1. And we compare this with the decision not to pay. And the decision not to pay is again the average of the payoffs, which is going to be minus 3 over 4 and minus 3 over 4, which is going to be minus 1.5 divided by 2, which is minus 3 over 4. So minus 3 over 4 is a less bad choice than minus 1. So in both cases, the government will choose, aggregately, to choose don't. In other words, don't pay the terrorists. Okay, so that solves for the two government choices. And the last node to solve is then for the militants. And the militants have a choice, looking first at the top, where if they don't take hostages, the payoff is 0. If the militants do take hostages, it's going to go through the government node to don't pay, and then into the not category, where the militants have a minus half. And 0 is better than minus half, and so the militants are going to choose don't take hostages. That's if they're hardline. If they're soft line, it's the same logic. If the militants take hostages, it'll be driven through these selected paths, and the militants will have a minus 2 1/4 payoff. If they don't take hostages, they're going to have a payoff of 0. So they're going to assign the green lines as their choice. So in this particular game, extensive form game, the militants will make a choice not to take hostages as a consequence of the government choosing not to pay. So this is how to solve the extensive